Let's now revisit again the first example that we looked at when we were creating our state space models. We have this simple spring mass damper system. We have already gone through the steps to derive its state space model. Now let's look at how do we convert that to the transfer function. And actually, we've already made the transfer function for this exact system as well. So we're going to be able to compare our conversion to the one we already know. And we'll look specifically, just in this example, for a mass of 1 kilogram, damping coefficient of 10 newton seconds per meter, and a spring constant of 16 newtons per meter. So we have numbers to work with when we go into MATLAB. But the process would be the same, despite what parameters we're using in the system. All right, so I want to get the transfer function of y over u. So again, y is the displacement. That is the one observable that we have as we scroll down to what we already have in our system. So we have our state equation, we have our output equation already developed here. So I want to take my A, my B, my C, my D matrices and convert this into my transfer function. But yeah, I need to keep in mind somewhere that what is my C matrix doing? Well, it's based on my state variables, what it's doing. It's going to be getting me x1, which is in my original coordinate system, y. So we still need to know how the state variables relate to the laboratory or the variables in our degrees of freedom, so we know how to interpret our results when we go into MATLAB. We're going to now go into MATLAB and let it do the conversion from the state space model to the transfer function model, but in the background, it's doing those matrix operations that were previously discussed. First thing I'll do is I will put in the specific parameter values for this demonstration so that I can numerically do this conversion. So putting in the m, the k, and the b values here. Then I'm going to enter the A, B, C, D matrices as we already derived them. So those are now in the system. So let me just make sure if I look at A, yep, it's 2 by 2 with the derived values. And B is a column vector because I only have one input in this system. C is a row vector and D is a scalar, 1 by 1, one observable, and one input. So everything is the correct size to now do my next step, where I'm going to let MATLAB do this conversion. So I'm going to run just this line and let's see what it outputs to us. So it gave us a B vector and an A vector. So again, what do these represent? Because this system has only one output or one observable and one input, B and A are both only a single row. A is going to have the number of rows equal to the number of inputs, 1. And B has a number of rows equal to the number of outputs, again, 1. And these are the coefficients in front of the S terms for the transfer function. So A will be the denominator. So working right to left, this means it will have 16 as a constant, 10s, and 1s squared, or just s squared, in the denominator. And B, working right to left, will have 1, just the constant, and that's it for the numerator. So I'll put it together now using the TF function, and we'll see in a little bit nicer form what does our transfer function look like. All right, so it says our transfer function is, just as I discussed, 1 over s squared plus 10s plus 16. If we compare this to the transfer function, at least in the general form for a spring mass damper, this is exactly right. We should be getting, for just a simple spring mass damper, 1 over ms squared plus bs plus k. Well, again, k is 16, b is 10, m is 1. So yeah, we are getting the same transfer function that we got when we derived this the first time, starting with the transfer function. And just to make sure, if I change this up, let's just say the mass is 3, make sure that everything is consistent here. Going through this. Now, actually, it looked a little bit different because it wants the leading coefficient of the denominator to always be 1 in the way it's representing it. But what did it do? This would have been a 3. It divided everything here by 3 in order to have this be consistent. So it basically multiplied top and bottom by 1 over 3, and it wants to express the transfer function in this form. But this is correct. I would have gotten 1 over now 3s squared plus 10s plus 16, and that would also be equivalent to what we're seeing here. So we just want to be aware that it's not necessarily going to look exactly like what we would expect if we derived it by hand, but it is going to be equivalent. So let me go back to a mass of 1 and get back to this system. All right, so back to the system at hand. So m is 1, b is 10, k is 16. So let's look at, before we go back the other way, 1, this is at least a correct transfer function, so that's good news. But let's see a little bit of how the transfer function relates to the state space model that we had. That's a little bit of a preview of, again, what we're going to see in Unit 2. Let me go back to this A matrix. Now, the A matrix is going to tell us about the stability of the system, both by its eigenvalues and its eigenvectors, again, as a little bit of a preview. So let's see what are the eigenvalues of this A matrix. So if I run it, it finds that they're real and they're unique and they are negative. They're in the left half plane. -2 and -8 are the eigenvalues of A. That doesn't mean too much to us right now. It will matter that they're in the left half plane. It will matter that they are real and unique when we get into the analysis. Now let's look at our denominator of the transfer function. Let me just bring it back up again. This s squared plus 10s plus 16, which a is just the coefficients of that denominator. What I can do is find the roots of the denominator, which we call the poles of our transfer function. So what are the values of s that make that denominator 0? I can use this roots function here and just put a in. I can put a list of coefficients and it's going to tell me the roots of a polynomial, which in this case will be the poles of the transfer function. Well, if we do that, it turns out the poles of the transfer function are also -8 and -2. The poles of the transfer function are exactly the same as the eigenvalues of that A matrix. But again, the transfer function model approach and the state space model approach are just two different ways of representing our same system. The system itself hasn't changed. We're going to look at the implications of this as we go into Unit 2. But we see that these two things are equivalent, the eigenvalues of A and the poles of our transfer function. At least for these linear systems that have a single input, that's going to be the case. All right, what if we want to go in the opposite direction? Let's look at TF2SS. So where are we going to give it? We're going to give it the numerator and the denominator of our transfer function, or transfer functions if we had like 2 rows for B. Just refresh ourselves. What is B? What is A? That's what we got out of SS2TF. That's exactly what we would have gotten if we derived this from the beginning in transfer function form. And let's see what this gives us for then the A, B, C, D matrices for the system. All right, if we look at D, it's 0, but we have some differences here. C1, it's giving us is 0, 1. B1, it's giving us 1, 0. We gave it 0, 1 as a column. And the A matrix, it's giving us -10, -16, 1, 0. Let me just do side to side A1 versus A. It swapped the rows and it swapped the columns on us. And for C, it swapped the columns. And for B, it swapped the rows. So it didn't give us back exactly what we started with. However, it is going to be the same system. Really, the difference it's doing here is it decided to swap out what our different variables were, or specifically what our state variables were. In C1, it's actually saying that the x1 is the velocity and the x2 is the position. And it consistently swapped the columns and the rows of all of the matrices to make that case. So it's not incorrect, but we just have to be aware that it is a slightly different interpretation of what the mapping is between our state variables, the x1, the x2, and what our original coordinate system was. So it's a little bit trickier to go from our transfer function form to our state space form because of these differences that it decides to put in there, rather than going from the state space form to the transfer function form. That's going to be a more straightforward conversion, but it is possible to go in the reverse direction. And we might want to do something like this for an electrical system where again the transfer function is going to be easier to derive, and we might then want to go into a state space form to do further analysis.